Hello, my name is Elisa Mendez, and I'll be presenting our work on eliciting confidence for improving crowdsourced audio annotations. Audio annotation is unique and should be studied on its own. It is a slower process because of the temporal nature of audio. Also, audio can be subjective, perceptual, or ambiguous. In real-world audio, multiple sounds can happen at the same time, making it hard to disambiguate one sound from the other, leaving room for annotator interpretation, increasing the chances of disagreement, and creating the need to quantify uncertainty in labels. Machine learning and crowdsourcing research have studied the use and collection of soft labels instead of hard labels, showing soft continuous labels provide richer training information and higher quality aggregate labels, leading to needing less data for training. We study this problem in the context of machine listening of urban sound because it has many applications where the data is ambiguous and the quality of the annotations highly impacts results. Some examples are 1. Urban noise pollution monitoring, which can help in developing plans for mitigating noise pollution. 2. Urban bioacoustic monitoring, key in understanding bird migration patterns. 3. Sound awareness tools for the hard of hearing, which can increase awareness of critical sound events for deaf and hard of hearing people. And 4. Machine perception for autonomous robots or vehicles, where incorrect predictions about the environment can potentially be fatal. We seek to investigate, does confidence elicitation for collecting soft labels affect individual annotation quality? Do the confidence elicitation method and aggregate label type affect aggregate annotation quality and cost? Our goal was to collect fine-grained probability estimates from an individual instead of a population. To collect labels through crowdsourcing, we created a web-based annotation application which had interfaces to support 3 annotation tasks, 1 for each confidence elicitation method. In all tasks, we ask participants to select yes or no about the presence of a jackhammer in the audio recording. Here, we show the direct elicitation method, where participants directly state using a slider from 50 to 100% in increments of 10 how confident they are in each label provided. These are then converted to probabilities and used as soft labels. If the presence of the jackhammer was yes, the probability estimates remain the same. If it was no, the probability estimates are calculated by subtracting the confidence from 1. For example, if the answer was no and the confidence was 60%, the probability estimate is 40%. We also proposed a betting mechanism where participants indirectly select their confidence by placing bets either on their heart label or on an X% chance lottery, playing 5 rounds from 50 to 90%. Choosing their heart label would mean that they are more confident in winning the bonus with their answer than winning a lottery with X% chances of winning. Collected labels consisted of a binary list where 0 meant they selected the lottery and 1 meant they selected their answer to the presence of the jackhammer. The switch from their answer to the lottery would indicate the confidence they have in their answer. After we did this process with all the responses for the betting task, we calculated the probability estimates using the same procedure as for the direct elicitation task. For both of these methods, we computed z-scores based directly on their confidence responses because the distribution of the collected labels depends on the personal interpretation of the scale presented. We refer to these labels as z-score derived probability labels. Here, we show the interface of the no confidence task, where only the binary question is asked. We studied 3 confidence elicitation methods, simple or direct, betting, and no confidence. We also studied annotation quality of the different annotation types, binary, probability, and z-scores derived from the probabilities. For each elicitation method, we averaged 1. The binary labels per recording, 2. The probability labels per recording, and 3. The z-score derived probability labels per recording. Finally, the aggregate labels were directly binarized using a threshold of 0.5 to form what we call hard aggregate labels. The non-binarized aggregates are called soft aggregate labels. We used Scaper to synthesize 10-second urban soundscapes with audio from Urban Sound 8K, a dataset divided into 10 cross-validation folds containing 10 classes. Our goal is to annotate the jackhammer. Each participant annotated 20 recordings, 10 folds at 10 participants per fold per task, total 300 Mechanical Turk participants. Now we show our results. In this figure, we compare the performance of the 3 tasks in accuracy, precision, recall, and depth measure. These results suggest that both the simple confidence and the betting mechanisms have better per participant performance in accuracy and precision than the no confidence method, suggesting that giving participants an additional step to provide their confidence increases annotator performance, as participants are allowed to change their answers to the binary question while they annotate their confidence. Also, these results suggest that eliciting confidence is beneficial even for tasks where the model is trained with only binary targets, like binary classification with a support vector machine or decision tree. To measure the effects of the elicitation method, annotation type, and their interaction on the quality of the soft labels per participant, we focus on the AUPRC metric that does not have a set threshold for binarizing the annotations. We found that the simple confidence elicitation method performs borderline statistically significantly higher than the betting mechanism. However, no significant effects were found for the continuous annotation types, probability versus z-score derived probability. Similarly to the previous slide, we measured aggregate performance with AUPRC as it does not depend on choosing a threshold for binarizing the labels. Each curve represents the average over 500 iterations when calculating AUPRC, where in each iteration we randomly order the participants per condition. For average binary labels, both confidence elicitation mechanisms produce aggregate labels of higher quality than the baseline no confidence method at all levels of participant averaging. Within each of the two confidence elicitation methods, we see that soft labels have higher quality than hard labels for all levels of participant averaging. In addition, much like the per participant results presented in the previous slide, when averaged over fewer participants, there is little difference between the two elicitation mechanisms. However, as we increase the number of participants, the quality of labels from the betting mechanism achieve higher performance than those for the simple confidence mechanism. To measure the quality of the soft annotations, we measured annotator agreement and as we increased the number of annotators and compared it to the aggregated annotations for all 10 participants. When comparing soft and hard aggregate label types for each confidence elicitation method and annotation type, we can see that agreement for soft aggregate labels is higher than agreement for hard aggregate labels at any number of participants, suggesting that using soft aggregate labels, we can collect annotations from fewer participants than if we use hard aggregate labels. The key takeaways are that similarly to previous work, we find that when using confidence elicitation methods, the resulting annotations have higher accuracy and precision when compared to those of the baseline, giving further evidence that collecting more fine-grained annotations is beneficial when dealing with ambiguous data. Also, because some mediums take longer to annotate, asking a bit more from individual annotators is preferable to having multiple annotators per data item. In addition, the methods we present offer a solution for collecting soft labels for binary and multi-label tasks. We propose the betting method as a way of collecting probabilities while avoiding directly asking participants for their confidence, since it has been shown that people misjudge their own confidence. Also, from preliminary data, it showed to be faster than the direct confidence method. It also resulted in higher quality aggregate annotations, with differences being more pronounced as more annotators were added. Finally, we evaluate our methods in an audio annotation task, which has applications to many important real-world problems, like noise pollution monitoring, urban bioacoustic monitoring, sound awareness tools for the hard of hearing, and machine perception for autonomous robots or vehicles. Moreover, the annotation methods are not limited to an audio use case. The confidence elicitation methods evaluated could be applied to other annotation scenarios where data can be ambiguous, binary, or multi-label, like tasks such as video annotation for visual object detection and tracking, or multiple evidence-based diagnosis.